We will work example 2.1 on principles and modern applications of mass transfer operations, written by Jaime Benitez, second edition. And here we're going to be working, as you can imagine, with unimolecular diffusion. Blood oxygenators are used to replace the human lungs during open heart surgery. So they is essentially an equipment. You can find them online. And the idea is to, of course, help or aid with oxygenation of blood. Oxygenation meaning addition of oxygen. To improve this design, you are studying mass transfer of oxygen into water at the, let's say, human body temperature, which should be something around 310 Kelvin, in one specific blood oxygenator. The correlated values, meaning that these come from a correlation of the mass transfer coefficient, is given as follows: 3.3 times 10 to the minus 5 m or meters per second. And you know this is not speed, this is related to this mass transfer coefficient. And they want us to calculate the corresponding mass transfer coefficient based on the mole fraction. So this is interesting. First we need to verify what type of units are these, and then we need to change them to mole fraction. And first, let us interpret this. Verify which type of units or which type of mass transfer coefficient is given. Remember, we can have concentration, molar composition, and concentration, molar composition, and I think, yeah, no partial pressure. Verify the type of process, either UMD, EMD, or other type of process. In this specific case, we are going to assume UMD, and calculate the required mass transfer coefficient in mole fraction of oxygen. So this is also important. It must be on oxygen. And why can we assume UMD is applicable? Because we can neglect the evaporation of water. So the solvent, water, of the oxygenator will be stagnant, or it will not diffuse. Diffusion of A, which will be oxygen, will take place. So oxygen thus goes into the water. Water stated must be stagnant, meaning no flow of air or no flux of air. Assume dilute solution, since the solubility of oxygen is very, very low at this temperature. I don't know about you guys, but most gases are not that soluble in water. And if this is true, we can use K-type coefficients, meaning that the classic coefficient for UMD must be true. Solution, the mass transfer coefficient value must be diluted. UMD must be basic. And K-type. This specified value is interesting. You can either go to the lesson right here, in which we have m per second, which will be, it should be something between, we have a simple option. Is it either this one right here or this one right here? So I'm going to assume this is concentration, and we gotta calculate the molar fractions. Another tip is, of course, learn by heart that this is by concentrations, meaning that if we want to change this concentration to molar quantities, we will need to use this equation right here. Essentially, what we need to do is to get Kx, which is molar fraction, equals K liquid, which is concentration, and its concentration. So, as you can imagine, we will need the concentration, but concentration was not given. So let me calculate the concentration of the liquid. Remember, concentration of the liquid will be the total amount of moles divided by the total amount of volume of the mixture. And the mixture, remember, is the solute, or oxygen, plus the water. And we know this is dilute, so technically we can ignore oxygen and just pay attention into water. Or if you want to account for oxygen, do it as well. I will not do it because this is literally less than 0.1%. So the mole of mixture will be equivalent to the mole of solvent, and the volume of the mixture should be kind of similar to the volume of the solvent. So the mole of mixture, I don't know if I was giving amounts, no. So what I will do is assume a basis of 1 liter. So 1 liter is, well, in volume, 1 liter. And in mass, I don't know, but I do know that density times volume gives me that. And the density of water at such condition is 993 grams per liter. So what I'm going to do is, okay, I will change or calculate the mass. So density is 993 grams per liter times 1 liter. I get 993 grams. But remember that I need moles, so I need to change those 993 grams to moles, which is what I'm doing here, dividing by 18, which is the molecular weight of water. I will get 55.2 mole per liter. And I don't know what type of units are we using here, meter second, so I can either use mole per liter or kilomole per cubic meter. So what I will do is just input this data, which is the concentration, times KL, and I will get my values in molar fractions.